everyone. Okay, thanks for coming for the class. Okay, I'm going to take your attendance first before we start, right? So just indicate that you're here. Okay, just indicate if you're here. Okay, right. Brenda, are you here? Brenda, are you here? Tan Su Pian, okay, Chia Chai Siu, Chu Zhang Hing, Chua Yu Yang, Ernest, Ernest, are you here? Ernest, Go Ken Sing, Go Ken Sing, Hu Hing Tong, Hu Hing Tong, Hu Bun Kyung, Lau Lok Jing. Okay, Li Zhe Lim, are you here? Lim Chun Wei, Lim Wen Yang. Okay, Lim Yong Chuan, right? Long Yao Ting, Long Yao Ting, good afternoon. Lo Tiong Lia, Lo Tiong Lia, Lu Chui Min, Ng Han Xiang, Ng Wei Hong, Ong Mei Lin, okay, Peng Shui Wen, Hua Yi Hang, So Yen Chang, right? Tan Xin Shen, Tan Xin Shen, Teo Yi Si, Wong Chung Yi, Wong Ka Sing, good afternoon. Yong Wing Liang, Yong Wing Liang, and Yong Chi Ye, Yong Chi Ye, Yong Chi Ye. Okay, let me check again. Ernest, are you here? Ernest, okay, good afternoon. Uh, Tan Xin Shen, okay. Yong Chi Ye, Yong Chi Ye, are you here? Everyone should be here. Yong Chi Ye, are you here? Okay, I'll check again later. All right, so today's class, we are going to review the materials that you have learned we're going to review the materials that you have seen in the lecture videos. Okay, now, week one, we looked at microcontrollers, we talked about development tools. Week two, we talked about GPIO. So now week three, we go into the processor itself, right? Because in order to write a programmer, you have to understand the processor architecture, okay? And the ARM Cortex-M processor architecture is a very good example because it has everything, okay? Now, if you learn processor architecture by looking at PIC microcontrollers, well, they are very simple 8-bit processor, so you're missing out on a lot of things. If you learn by looking at those Arduino, Atmega processors, you're also missing out a lot. Okay, there are a lot of features that are not there. But if you study Cortex-M processor architecture, you are learning almost everything, in fact, everything. Okay, because it is the most advanced, most complex microcontrollers processor architecture in the market. Okay, so you learn everything. All right, so now, what's it all about? Uh, it's actually a system on chip, right? In the old days, we designed an entire circuit on a printed circuit board. So in the old days, when Steve Jobs made the first Apple computer, right? It's actually a printed circuit board. You have one IC for the processor, one IC for the interrupt controller, one IC for the IO port, one IC for memory, etc. So it's all on a single board, very big. So the computer is very big. Nowadays, your handphone might be more powerful than your desktop computer or your laptop. The latest flagship handphones. Why? But it's so small, right? Why? Because of a system on chip. Right? It's because of a system on chip. You see, the entire everything on the circuit board is integrated into a single IC. Right? This technology is called system on chip. Brenda, can you see my screen? I'm presenting now. Can you see my screen? No. Okay, let me stop my presentation. I present again. Okay, wait. Can you see my screen now? Right. So let me know if you cannot see my screen. I always presenting my screen. Okay. So we were just here on this page. Just now I was talking about the good old days, not good old days. The old days it's like this, right? Nowadays it's like this. So instead of a circuit board, you have a single IC. So a single IC, you have a lot of advantages. The advantages are you minimize the cost. Right? You minimize the cost. That's the most important advantage for economic reasons. It must be cheap. And on top of that, because it's so small, power consumption is also very low. Okay, and it can fit into small devices. So you have lots of portable gadgets today because of system on chip technology. So what's on a system on chip? System on chip, it contains digital and analog parts. Digital and analog parts. Now you cannot create a circuit entirely using digital circuit. Digital circuit is your logic gates and flip-flops. Okay, imagine your transistors. You see, at the lowest level, it's a transistor. You combine a few transistors together, you get a logic gate. You combine a few logic gates together, you get a flip-flop memory element. You combine flip-flops and logic gates together, you build a digital electronic circuit. Okay, so the most complex digital electronic circuit is your processor. It's the most complex. Okay, there are others. So you have you have a digital block here for your processor, and then maybe you have digital blocks for your I/O port, your serial ports, your timers. Okay, but you can't run away from analog. You cannot build your entire circuit from digital parts alone. You must have analog. What are the analog parts? The analog parts are, for example, your power management circuit. Okay, power needs to go into your mouse controller, your VDD and VSS. The power goes in, and then this power needs to be distributed. So you need to have small capacitors, resistors, electric circuit inside. So that's what we call your analog circuits. Analog circuits can also be mixed together with digital circuits. If you have that, we call that mixed signal circuit, mixed signal. And you need that for ADCs, DACs, radio transmitter receiver, because these the what goes out is analog, but what comes in, the analog needs to be converted to digital. So we call these mixed signal circuits. Okay, and all these blocks, these digital and analog blocks, right? All these blocks, they are extremely complex. So some companies make it a business to design these blocks and sell the design. Okay, and all these blocks are connected together by buses. The bus itself is another block. I didn't draw that, but the bus itself that connects all these blocks is another block. So all these blocks, because they cost a lot of money to develop, so the companies that develop them hide the internal contents. So you can't reverse engineer, you can't see what's inside. You know, like you buy the Windows operating system, you have no access to the code. Okay, they don't want you to see the code or modify it. They just sell the product to you uh, locked. So the design inside, the circuitry inside is locked. Is presented to you as a black box. So you know what is the input, you know what is the function, how it will convert the input to outputs. For example, black box design like this. For example, your processor. So your processor, you got inputs, right? Which is data, addresses, and then outputs is the data that the processor has computed. It produces outputs. Right? That's a simplified view of it. So these designs, they are protected by law. We call that intellectual property. So these blocks are called IP blocks or IP cores. Okay. So if you learn digital system design, if you learn digital system design, you are from electronic stream, digital system design, you program these blocks using VHDL. Yes, electronic system design. the subject, you learn to design blocks like this. Okay, you don't, because it's so complex, so you don't need to draw the logic circuit inside anymore. In in your diploma subject, digital electronics, you learn how to build a digital circuit by drawing the truth table and then creating the K map and then writing out the equation which you can implement in logic gates. But imagine a designer that have a few thousand logic gates. You won't do that anymore. So you will design the behavior of the digital circuit using hardware description language, HDL, or your VHDL, very high speed integrated circuit hardware description language. So you use that to design what is inside. All right. And then the VHDL language, it will convert VHDL, your VHDL programmer will be used to synthesize the logic gate. Right? So that's another development tool. In my subject, you learn Kale microvision, right? You got compilers. Compiler is a program to convert your C language high level to object code, right? That's a program development tool. So VHDL, you also have development tool to convert your hardware description language to the logic circuit, the synthesized logic circuit. Okay, so this is uh, this is this is that. So if you're a hardware description language HDL engineer, you're a engineer who writes VHDL code. So you design what's inside. Okay. So if you go to company Intel, if you go to Intel as a graduate, you won't do this. This is design work. You will work as a test engineer. Test engineer means you write code to test this black box. You don't know what's inside the black box. You just write a C programmer that will feed input automatically into this black box, and then you check whether the output is correct or not. Why do we need to write a program to do that? Imagine if the input got 1 billion combinations. If you build a digital circuit with 4 inputs, you got 16 different combinations. You can test that out one by one. But if you got a few billion combinations, you're not going to test that one by one, right? You're going to write a program that will feed the input into the black box, and then you're going to check the output whether it's correct or not automatically. And then you run the program, and the program will run for a few days. Worst case, maybe a few hours. Then you find an error, then you have to tell the design team, there's an error with this particular input, it gives the wrong output. Okay? So then the design team, that's the engineer who writes the VHDL code to create the function. Then he has to look at his design and modify. Okay, so that's what ARM does. ARM, their main job, their engineers is they design the they write the hardware description language to create the processor, right? And it's not one person. The processor is extremely complex. You may have a few hundred engineers working for a few years just to come up with one processor design. Okay, and inside the processor you have a lot of parts. You look at the processor as one block, but inside the processor you have hundreds of components. Each component is built by one or more engineers, and you combine everything together, you get this single black box. Okay, so ARM, what they do is they sell their processors. And the processors that ARM sell, last time they have very complex naming conventions. Last time they got ARM 7, ARM 9, ARM 11. The name very complex one. So now they simplify everything. They call their processors ARM Cortex A, right? ARM Cortex R, and Cortex M. So what's the difference? So you see, nice play of words, ARM. So A is for application development. Application development is high performance, multimedia, video processing, graphics processing, uh, to run for your tablets, smart devices, smart TV, smartphone. Use Cortex A. Right? Cortex A can run a full Linux operating system from high performance. Right? It can be clocked up to gigahertz clock speed like your desktop computer. Okay? Then Cortex R, the R stands for real time or reliability. This one, Cortex R is used for those systems that needs to be very reliable. Okay, the system must respond in real time. You feed it input, it must respond output immediately, real time. These systems cannot fail. For example, aircraft control systems, transportation control system, satellite communications, medical equipment, Cortex-R. Cortex-M, M stands for microcontroller. M stands for microcontroller, consumer product. All your industrial consumer products, all those electronic smart gadgets in your house, like your vacuum cleaner robot, your all those IoT devices, okay, like the Daikin air conditioner that you can turn on and off with your smartphone. I just heard that on the radio. You can, you can. This lady was saying, talking to her husband, "Hey, why the aircon turn on by itself?" Then the husband said, "Oh, because I use my smartphone to turn it on." Advertisement, So all these are Cortex M. So we don't look at A and R, we look at M. Right? It's upwards compatible. A is the most complex, M is the least complex. So we look at M, and M itself has three separate architectures. Okay, the blue color one here, the architecture is called ARM version 6M. The green color one is ARM version 7M, and this orange color one is ARM version 8M. What's the difference? Why got version 6M, 7M, 8M? The difference is the instruction set. Okay, the version 6M architecture, the processor has the smallest instruction set, means it can do the least operations. Version 7M have more instructions. What are those extra instructions for? Data processing. Okay, data processing, dealing with images, audio signal, video signal, graphics, um, floating point numbers, more high performance computing. Okay, that's 7M compared to 6M. And then 8M further built on 7M by adding security and AI. Co-processor is AI. What do we mean by AI is you see, normal processors they are not good at dealing with audio, video signals, right? All these signals are that huge amount of signal coming in real time. You need to process it and produce the output immediately. Okay, normal processors are not good at this. So there are special processors that are specially designed to deal with this type of operation. Okay, for example, in your computer, you got your graphics card, your sound card. These are specially to deal with audio and video signals. Okay, so it's the same with microcontrollers. Nowadays, microcontrollers they have an additional processor, a co-processor. So it's just like your sound card, graphics card. This co-processor is used for machine learning. Machine learning, what is machine learning? Is actually a program that deals with, it's actually a neural network program. Machine learning is actually a neural network program. It's a program that consists of a lot of math equations that implements a neural network. So when you feed in data, it will give you a result. It will tell you whether the data corresponds to A or B. For example, you teach it, this is a dog, this is a cat. So you give it 1,000 images of a dog and 1,000 images of a cat. So as you feed it with images, the neural network that is represented by a set of math equations, the math equations will have coefficients. The coefficients will change as you teach it, so that at some point you feed it any picture, it will tell you whether it's a dog or a cat, right, based on this neural network. So you can see the neural network is actually consists of a lot of multiplication and addition operations, all done in parallel, very fast. So machine learning is actually parallel processes. Okay, the co-processor that helps the main processor to run the machine learning, those neural network algorithms, it actually consists of a lot of parallel processors, small processor. In your Cortex M processor, you got one main ALU, your main ALU, the big ALU. Okay, the co-processors they got a lot of small ALUs, maybe 50 to 100 ALUs, which allow you to process information in parallel very fast, which is what we need for machine learning and digital signal processing. Okay? So, and that's the co-processor. Security is for IoT. industry that develop products that meets the current demands. Current demand is for IoT. IoT data security is very important. So security is just ARM version 8M provide you with additional instructions to encrypt and decrypt data. And so your processor got some extra hardware that can encrypt the data as it goes out. And when the data comes in, it can decrypt the data. Using hardware means faster. If you use software, it's very slow and very power inefficient. So you use hardware to do things that is the fastest and the most power efficient. Okay, so we have these three families. The difference is just instruction set. So we learn for this subject, we just look at ARM version 6M, the basic instruction set for general purpose data processing. Okay, this version 6M is a direct, you can use it to directly replace 8-bit microcontrollers. So if you're very used to using 8-bit PIC microcontrollers, then you can very easily change to version 6M microcontrollers. For example, Cortex M0 microcontroller, M0 Plus, and M1. Okay, so in version 6M architecture, we got three different processors, M0, M0 Plus, and M1. All got different application. All of these got different application on it. So M0 is the cheapest. M0 Plus is the most power efficient. M1 is a soft core processor. It's for you to put in FPGA. Okay, for you to put inside FPGA. So M1 is not a physical processor. It's a processor in VHDL code. So you can program part of your FPGA. FPGA is a special chip, field programmable gate array. It's a special IC with a few 100,000 logic gates, all not connected one. So when you download a VHDL program inside, you can configure its connections to perform some certain operation. So if you download the Cortex M1 design into an FPGA, then the FPGA will become a Cortex M1 processor, right? And then your FPGA still got a lot of space on, so you can put in the I/O port, you can put in the timer, you can put in different things. So in other words, you can actually program an FPGA to become a microcontroller. Not really, because you still need analog. So FPGA is entirely digital, got no analog parts one. So you need analog for power management for ADC, DAC. So that is why you cannot fully program an FPGA to become a full microcontroller. Maybe you can program FPGA to speed up certain operations as a co-processor, but not as a full microcontroller, right? So then here we got M3 is the general purpose guy, M4 is for digital signal processing, M7 highest performance. Out of all the Cortex, M7 is the highest performance. Okay. Then you got M23 is for IoT. For IoT applications is the smallest and lowest cost. Okay. Then if you need DSP, you get M33. If you need physical security, physical security means nowadays people they can buy your, let's say you sell a product, inside you got a processor, and then inside your processor you got some program which you spend a few years developing. People can actually buy your product, then they can take your IC, they can cut off the top, the protective layer of the integrated circuit, then they use a microscope to look inside and reverse engineer your design, okay, physically. And there is no way you can stop this using software means encryption, decryption, no use, because they physically cut open your design and look inside using a microscope. So what they do is we call this hardware security. Hardware security means tamper proof. If people try to cut open your design to look inside, there are ways that you can stop this. Right? That's what we call M35P. P means physical tamper-proof security. Right? So that's what M35P have on top of M33 hardware security. And M55 is the latest guy with machine learning. This is the latest, I think, released last year. So maybe there are no microcontrollers using this processor yet. They just released it, so people are understanding how to use it before they can actually develop a microcontroller with this processor. Okay? And then the next direction after this is multi-core processor, life gets more complex. Imagine you have to write microcontroller programs to run on multi-core processors. So that's the next step. So now if you look at this, I ask you a trivia question. Trivia question. So we got M0, M0 plus M1, M3, M4, M7, M2, 3, M33, M35P, M55. Which one do you think came out first? Don't Google. You just think about it logically. If you are an entrepreneur, you open let's say you are some top researcher in Intel. You have lots of experience in IC processor design, and then you want to open your own IC processor company. So you want to develop your first processor to sell. Which one will you develop first? M1. Why? Why M1? M0. Why M0? Why M0? Now this actually they are all programmable. They are all programmable. Fast fast prototyping is near there. Start from zero. Okay, you see, I like to ask this type of questions in the exam. I ask you, which one do you think it is? And then can you explain why? Low cost. Now, if you think about it, when we do business, the most important aspect of business is profit. Profit, right? Because if got no profit, you can close shop already, must have profit. So if I know I want profit, how do I maximize profit? By selling a product that the most people can use, right? I need profit. So I understand that. Then I must maximize my profit. How I maximize my profit? I must sell something that the maximum amount of people can use, right? Which is the product that the maximum amount of people can use? Is it the smallest? Is it the highest performance? Or is it the general purpose? Yeah, you are right. Exactly, M3. So M3 was the first device, general purpose one. So they test the market with the general purpose guy, and everyone loved it. It was very power efficient. It was very powerful. And then the things start to come up. People use M3 and then they ask, I like this very much, but I want something that is more power efficient. Can you do it for me? Yes. Then they made M0, M0 Plus. And then people that use M3, they like it very much. Then they say, can you make something that is higher performance? I'm saying, no problem. Then they made M4 and M7. Okay. And then got M4 and M7, very nice, high performance. Then people ask, is high performance? Yes, but it's still not fast enough to do AI. Can you help me? Yes. Then they came out with co-processor for machine learning and security for IoT. So you see, the new products all come out because of a specific need, right? Now let me show you an example why we say M0 is the smallest compared to M7, highest performance. What is the difference? Okay, you can type CortexM developer, right? Just type CortexM developer. Right? You are a developer. You want to use CortexM devices. Okay, CortexM developer. So I see here. So you got M55, 35P, 33, 23, M7, M4, M3, M1, M0 plus, M0. Okay, let's look at M0 plus. The most or M0. I look at M0, the smallest. So read more. M0 is the smallest. I compare with M7, the highest performance. Yeah, let's compare them. So I put them side by side. This is M0 and this is M7. Let's compare them side by side. So what do I want to compare? I want to compare size. We say size, man. What do we mean by that? Okay, let's compare their size. So this is what's inside. This is what is inside the processor. So you got the interrupt controllers, right? You got this is the processor core. Then you got memory protection unit. This is the bus. This is cache. You got debugging. This is all for debugging. And then you got the DSP coprocessor, floating point coprocessor. This is JTAG, also for debugging. And this is your bus. XC is your bus. So you see there are a lot of components. Now I was saying the processor got lots of components. And inside each of these guys, you can break it down into even smaller components. Okay. So when you compare M7 and M0, M0 is much simpler, right? So this guy got a lot more things. M0 is lesser. Okay? Which is why M7 is bigger, more power consuming. M0 is the cheapest. So we see why is it the cheapest, smallest. Okay, we compare this one. This is the implementation. Like this. Now, if you compare two things, you must compare apple to apple, right? So we compare the size. This is the technology. This is the technology. So you guys are learning microelectronics this semester, right? Microelectronics or CMOS designer microelectronics. So this is 40 nanometers. Okay, 40 they've got different technology. So we compare the M7 40 nanometers. LP means low power. Okay? We compare the M7 40 nanometers with the M0 40 nanometers. Okay, what is the difference? Okay, so let's see. Let's look at size. M7, the size is 0.1 mm square. 0.1 mm square. That means you imagine a square 0.1 mm times 0.1 mm. That is the size of your IC. Okay? You imagine. You look at the palm of your hand or you look at your finger. You imagine a square where the side is 0.1 mm and 0.1 mm, a square 0.1 mm. So 0.1 mm times 0.1 mm is 0.1 mm square, right? That's the size. Okay. You compare with this M0, 0.008 mm square. That's like how many times? How many times smaller? 15, 16 times smaller, right? 15, 16 times. 100 divided by 8 lah. 100 divided by 8, about 15 to 16 times smaller. So Cortex M0 is 15 to 16 times smaller. And then you see the power consumption, 5.3 microwatt per megahertz. That means if you clock the processor at 1 megahertz, it's going to consume 5.3 microwatts. While this processor, if you clock it at 1 megahertz, it's going to consume 58.5 microwatts. So about 15 to 16 times more power and 15 to 16 times bigger. Okay. What if you want to imagine what does 58.5 microwatts means? What means what is not as small as a Tesla. Yeah, that's got different size. Anyway, it's just a small dot. Anyway, okay. Power or watt is equals to I times V. Current times voltage, right? Current times voltage. So if your microcontroller voltage is 3.3 volts, so 0.0000585. This is microwatts. 0.0000585 is 58.5 microwatts. So is equals to current multiplied with voltage 3.3 volts. Okay, so current is equals to 3.3. Current is equals to 0.0000585 divided by 3.3. Okay, that's your current. So your current is probably about 58 divided by 3. About 20 microamps. About 20 microamps. 20 microamps. Okay, so if you got a battery, let's say you got a battery that is 2000 You got a lithium ion battery. You got a lithium ion battery. It's 3.3 volts, 2,500, I give easy to count, 2,000 mAh. You got a battery, 3.3 volts, 2,000 mAh. That means the battery can produce 2,000 milliamps continuously for 1 hour, or 2,000 mAh is equals to 2 million micro Ah. So it can produce 2 million microamps continuously for 1 hour. So 2 million microamps divided by 20 microamps, that's 100,000 hours. Okay, so if you have this battery, your processor can run for 100,000 hours. 100,000 hours divided by 24 is 1 day, right? So how many days is that? How many days is that? 100,000 divided by 24. So that is 4,166 days, which is roughly divided by 365, about 11 years. Okay, so that's how we calculate. So you can see, this is M7, not M0. M7, M7 can run for 11 years. M0 can run for 11 years times 16, 100 years. Is it correct? 11 times 16, something like that. So basically, and that is why nowadays electronics are going into energy harvesting, okay? Because those small sensors that you can put all over the place in the environment, because they draw so little power, you can actually power them from energy in the environment. You can power them from vibration. For example, those bridges, or your car tire is constantly moving, right? So you can put tiny sensors inside. The sensors can extract energy from the vibration of the tire and then collect information about the tire, whether the tire is cracking or the pressure inside is high or low, etc. So you can monitor everything with tiny sensors that extract energy from the environment, and these sensors can run forever. Okay, because of this. Okay, so I just want to talk about that. Let me just close this. Right, so this now, so we will start our discussion with Cortex M0. All right, and the Cortex M0 we discuss by looking at its instruction set. Because how do you use a processor? By giving the processor instructions. All right, how do you use a processor? You tell the processor what to do. How do you tell the processor what to do? You tell it what to do using assembly instructions. Each processor is designed to understand a set of assembly instructions. So Cortex M0 is designed to understand 55 instructions, the basic instructions, 55 instructions. So how do you use the processor? By telling the processor what to do with these 55 instructions. Now, what does the processor do actually? This is a simplified view of the processor. What the processor basically does is, it will load data from memory, load data into registers, okay? And then the ALU will perform operation on those data. Once you are done, the ALU result is stored or written back to memory. So that's all a computer does. That's all a processor does. It reads data from loads or read data from memory, perform some operation on them, and store it back to memory. Okay, but the processor, in order to speed things up, it doesn't operate on data from memory directly. The ALU can only perform operations on data in registers. So you have to load the data into registers first. Okay, now the registers here, what are they? The registers here. The registers here are, we call it a register bank. You got 16 registers. So you got the low registers and the high registers. R0 to R7 are the low registers. R8 to R15 are the high registers. Okay. Now, the R0 to R12 are general purpose registers. R13 is the stack pointer, R14 is the link register, and R15 is the program counter. What's so special about them? The stack pointer is used when you do push and pop. Okay, when you do push and pop. You see, if I execute this instruction, push R1, I push the contents of register R1 into memory, into the stack, to the stack. So where is the stack? The stack is wherever the stack pointer is pointing to. The stack pointer is just a register holding an address of memory where the stack is located. So the stack pointer is holding the address for this particular location right now. So this is the stack. Now when you push something to the stack pointer will decrement first, -4. Why? Because 4 bytes. Each register is 4 bytes. So it will -4 first, and then the Y goes in. Okay? If you pop, it's the other way around. Wherever the stack pointer is pointing, the contents will be popped into whichever register you use in your instruction. So if you say pop R2, then Y will go into R2. Pop R3, then Y will go into R3. After you pop, the stack pointer will automatically increment by 4, +4, go up. So you pop again, something come out, then you go up some more. So when you push things in, the stack grows downwards. When you pop things out, the stack goes back up. Okay, so that's the use of the stack pointer. Now the link register and the program counter, these are used for addresses. What do we mean by that? Program counter always tell you the next instruction to execute. We always tell the processor the next instruction to execute. For example, if you see here, okay, this is address X. So this instruction is 2 bytes. So the next instruction will be at X plus 2. After that, the next instruction is at X plus 4 and so on. Now, this particular instruction is a program branching instruction. Your program will jump somewhere. How does your program jump somewhere? Branch to Y. I want the program to jump here. Okay, but the next instruction my processor executes should be at this one, X plus 2. How does it go to Y? Very simple. We just modify the program counter. So the program counter is initially having what X plus 2, next one. When you execute a branch instruction, it will modify the contents of program counter to Y. So after you execute this instruction, your processor's next instruction is here. Okay, and this one will incur 3 additional cycles. 3 additional cycles. Why? Because you see, this is the processor pipeline. This is your processor's pipeline. You fetch an instruction. Now your processor can fetch 32 bits at one go. It's a 32-bit processor. Can fetch 32 bits at one go. So let's say we are using 16-bit instructions. So you can fetch 2 instructions at one go. Fetch instruction 1, fetch instruction 2. Then it decodes instruction 1. When it executes instruction 1, it will decode instruction 2. But when it executes instruction 1, it finds that this is a program branching instruction. That means instruction 2 is not the correct instruction, so it has to refetch the correct instruction. So we say flush the pipeline. Remove everything from the pipeline, flush the pipeline, refetch the correct instruction, then you decode the correct instruction, then you execute. So effectively, if you have a program branching instruction, it will incur a 3-cycle penalty before the correct instruction gets executed. Okay. Now this is for program branching. If you have a data access instruction, so I fetch the instruction, I decode, I execute. When you execute and the processor finds it is the data access instruction, that means I need to access memory, whether it's a read or a write. I need to access memory. So the pipeline needs to be stalled for 1 cycle because the memory access will take 1 cycle, whether it's a read or write. Okay, the data transfer is 1 cycle. But if your processor has a write buffer, okay, then you don't need to stall because the processor can, instead of waiting for the 1 cycle for the store operation to complete, the processor can just send the data to the write buffer. The write buffer will then take 1 cycle to write it to memory, while the processor can go on doing the next thing. So, but read cannot. Read, load, you have to wait until you get the data before you can proceed. But write, you can just write the value into a write buffer and proceed. So if you have a write buffer, then there will be no pipeline stall. Okay, right. Now, what if uh, what if I want to come back? What if I want to come back? Branch is a one-way ticket. You go there, you can never return. But if I want to come back, then I use BL, branch with link register, BL. The link register is used to store the return address. So before you modify the program counter, before you modify to jump to Y, before you jump to Y, the address of the next instruction X+4 is saved into the program, is saved into the link register. So the link register is used to store return address for function call. Functions that return by this. Okay, so you BL branch with link register to Y. So you modify your program counter to point to Y. At the same time, the return address is saved into link register. So then, because program counter changed to Y already, so the next instruction will be add Y, which is this function, and you call this function. So you execute the function code, and then at the end, when you return from the function, how it's implemented is you use a BX instruction, branch to the address in this register. The BX instruction allow you to branch to the address stored inside a register. So LR stores this address, right? So if you branch LR means that you branch to here, so you return back where you call. Okay, so when you use function, whenever you write function calls in your program, C program, it's actually going to be compiled into BL and BX. This is how you call the function. This is how you return from the function. Okay, so that's I want to explain this one is for the SPLRPC. Okay, so now you know these registers. Now, and here, so you know about the register, bank 16 register, stack pointer, program counter, LR already. Then we have the XPSR. This is the status, program status register. Program status register, I just show you the result of your operation. You know your ALU, when you perform an operation, the result can be negative, it can be 0, you can have a carry out from your most significant bit. So all these, we call these ALU flags. They are stored inside the program status register. Okay, we'll come back to this. We'll come back to this program status register. Now, PRIMASK, this is the priority mask and control register. These two guys, what do they do? Okay. The priority mask is this register got 32 bits, right? But actually you only use 1 bit. Global interrupt, enable, disable. Okay. Mask means block, mask, cover, block, masking tape, you cover something. So if you put 0, nothing happened. If you put 1, means you block all interrupts from reaching the processor. Global interrupt disable, block all interrupts from reaching the processor. Right? This is the master switch. Like the fuse box in your house, you got the main fuse. You close the main fuse, you switch off all electricity in your house, right? This is the main fuse for interrupt. Okay. Then you got another guy, the control register. This is the priority masking. Then you got the control register. Control register got 2 bits. The first bit is to select privilege. The second bit is to select the stack. Okay, why do we want to select privilege and select the stack? This is for operating system. We come to this in week 7. So now we if you don't use operating system, we don't use the control register. We don't care about it. Okay, so stack and privilege are these for operating systems. We come back to this on week 7. Okay, so here, where will we are? We are here. So now we talk about so this is your CPU, you got your registers, you got this is your register bank, and then you got your other registers, ALU and control unit. Okay, this is where interrupts come in. Right. So we come back to the question. What does the CPU do? The CPU execute instructions. So we look at some simple instructions. The most basic instruction is instructions to move data. Instructions to move data. Okay, so move data where? Between CPU registers, and between memory and CPU register. So you use these instructions to move data from memory to register, and you use these instructions to move data between registers. Okay, so this one is you move from special register to normal register, move from normal register to special register, MRS and stuff. So the special registers are your XPSR, premas, and control. Okay, now registers why you need these instructions is because CPU registers don't have address. You learn in C programming that if you want to access memory, you can access if you know the address. You can use a pointer to access memory if you know the address. But CPU registers, right, R0 to R15, control, pre-mask, XPSR, these guys, they have no address. So how do you access a register that have no address? You have no other way except programming in assembly. So you must program in assembly. But the development tools provide you with some special functions. These functions are in this file. So when you build your project, you see there are some header files that are added to your project. These are the guys. So this core underscore CortexM function.h. These are some C functions that you can use to access these special registers. For example, get priority mask, set priority mask. So you can use this in your C program to access the priority mask register and also all the rest. Okay. All right. So how about memory? You got a few instructions to move data between CPU and memory. Okay, you got single data transfer and multiple data transfer. Now, single data transfer is like this. LDR, for example here, LDR, the address in R7 to R4. Okay, so R7, let me zoom in a bit. What it means is R7 holds the address of the location that you want to access, and then that location you move the data, load it into R4. Okay, so you can load the entire 32 bits, or you can load 16, or you can load the entire 32 bits LDR, or you can load 16 bits LDRH half word, or you can load 8 bits LDRB byte. Similarly for store, you got STR, STRH, STRB. Okay. Now, if you see there is a S here, this is called sign extension. Sign extension is if you're dealing with negative numbers. Because if you're dealing with negative numbers, they are in 2's complement. The most significant bit is a 1. But if you move this 16-bit value to a 32-bit container, the most significant bit will be zeros, right? So then your value, the sign will be wrong already. So you have to use a LDRSH sign extension. When you move this 16-bit here, the most significant bit, which is a 1, because it's a negative number, let's say, is duplicated all the way. So you get all ones here. We call this sign extension. LDRH is 0 extension. LDRSH is sign extension. So you need it if you're moving data from a smaller container to a bigger container. So you need it for byte as well, half word and byte. Okay. Now this is single data. How about multiple data? Multiple data, for example, load multiple, right? From memory starting at this address. So R0 is, we call it the base address. The base address. R0 holds the base address. Right? So you load the value into R0, R3, R5. Now the sequence doesn't matter. The lowest address will always go to the lowest number register. So you want to load 3 pieces of data from memory starting at this address into R0, R3, R7. Now R0 doesn't change. R0 will still hold this address. If you want R0 to update, you put an exclamation mark there. Then after the operation, this register will update. So here I'm moving R2, R3, R4, R6. So after you finish this load multiple operation, R1, the value will become the original value plus 16 already. Okay, you updated. Right. Okay, so we have looked at the materials for this week. Now let's quickly run through. It's very fast, just a few minutes. Let me run through quiz 3 with you. So let's look at the first one, the first question. We have an energy harvesting sensor that you want to implant into the body. So here we got a hint already. We want to implant a sensor into the body to monitor the cellular temperature. This is for some cancer research. They want to see if when the cancer cells spread, does it increase cellular temperature? If so, then we can detect the cancer cell spreading by implanting these sensors into the body. So the sensor must be very small and very low power, right? Because energy harvesting. So which one is the most suitable? M0 plus, lowest power. Okay, obviously, we won't use M7 or M4 or M35P for this application. We want smallest and lowest power, M0 plus. Then, next one. Why is the value in the link register always incremented by 1? Why is the value in the link register always incremented by 1? Just now I forgot to mention this. I forgot to mention this. You see, your instructions are 16 or 32 bits. Your instruction are 16 or 32 bits. Okay, so if you put 16 or 32-bit instructions in memory, they will always either use two containers or 4 containers, right? So they will always start from an even numbered address. Because it's either 2 container or 4 container, they will never start from an odd number. So the LSB is always 0. If the LSB is always 0, then we don't waste it. We can recycle it for some other purpose, right? So it is recycled for the purpose of indicating whether the instruction stored at this location is it a thumb instruction or a legacy ARM instruction. Legacy ARM instructions are the old ARM CortexM process, the old ARM processors 32-bit ARM processor instructions, the old ones. The newer ones are called thumb instruction. So for those processors that support the new and the older one, so you need to specify here whether it's 0 or 1. But for CortexM, CortexM only support thumb instruction. That's why it must always be a 1. This bit is always a 1. So you know the link register is used to store the return address, right? The link register is used to store return address. The bit 0 must always be a 1 because you can only execute thumb instruction. You cannot execute ARM. So it indicates that it is not ARM state. It can either be thumb state or ARM state. Right? It cannot be ARM state, so it must always be incremented by 1. Right. Next one. If I push R7, R5, LR, which is correct? Which is correct? If I push R7, R5, LR. Okay, now let me draw this out. Let me draw this out. Let me draw this out. So this is your stack. Okay, you push something into memory. So your stack pointer is pointing here, right? Stack pointer is pointing here. If you push R7, R5, LR, it will go in like this. R5 will go in, the lowest go to the bottom, R7 and LR. Why LR is the highest? Remember, LR is R14. LR is actually R14. Okay, so this will be SP minus 4. This will be SP minus 8. This will be SP minus 12, right? Okay, so which of the following is correct? R5 is stored at address SP minus 4, wrong. Okay, R5 is stored as, no, this is not correct. Invalid, LR is pushed in last. R7 is stored at, this is the correct one. Okay, R7 is stored at SP minus 8. Actually, there are 2 answers here. LR is pushed in last or R7 is stored at SP minus 8. Both are correct. Why that? Because the bottom goes in first. When you push multiple data in, the bottom goes in first. If you put one at a time, of course, it's LR. But if you push multiple, R5 go in first, then R7, then LR. So you got 2 answers. LR is pushed in last or R7 is stored at SP minus 8. Okay? All right. Next one. Consider this instruction. What is the value in R0 after you finish executing? R0 will update, right? R0 update. So how many here? R1, R2, R5, R6, R7. R1, R2, R5, R6, R7. Got 5. 5 times 4 is 20. So it will be, after you finish this instruction, R0 will be updated to R0 plus 20. Okay, pretty straightforward. Right? Okay, next one. Why is LDR-SB faster than LDR-B? Because LDR-SB performs sign extension. If you use LDR-B, then you have to additionally do sign extension. You have to write a few more instructions to do the sign extension, right? But if you use LDR-SB, you automatically do sign extension for you on the fly data processing, right? As you load the data in, the sign extension will be done automatically on the fly. So that's why it's faster than LDR-B. Okay. Uh, STR may execute faster than LDR. Why? Because LDR, you always have to wait one cycle for the data to be loaded. But STR, if you have a write buffer, then you don't need to wait. You can immediately proceed. So STR, that's why you can execute faster than LDR. No need to stall the pipeline because if a write to memory is buffered, you can buffer the write to memory. Then you can go on without waiting for the store operation to complete, right? Load, you must always wait for it to complete. Otherwise, you don't get the data. You need the data to continue, man. So you have to wait for the load operation to complete before you continue. But write, you don't need to if you have a buffer. Okay, next one. If contents of address 0 is this value, where will the second item be located? Now, address 0, address 0 stores the stack pointer. So if the stack pointer is 20008000, if the stack pointer value is, if the stack pointer value is 20008000, if this is the stack pointer value, then this will be the first stack item located at, the first item will be located at 20007FFC minus 4. Then the second item will be located at 20007FF8. Right? The second stack item will be located at 207FF8. Right? Okay. Last question. Why are some instructions restricted to using the low register operands only? Because your 16-bit instruction don't have a lot of space. Your 16-bit instruction don't have a lot of space. So if you use the higher registers, okay, register, if I use R0 to R12, then how do I encode it? R0 is encoded as 0000. R12 is encoded as 12 is 1100. So I need 4 bits, right? But if I only use the low register operands, low register operands is R0 to R7, R0 to R7. Then I only need 3 bits to represent each of them. R0, I only need 3 bits, and R7, up to the maximum R7, I only need 3 bits. Okay, so some instructions, the 16-bit instructions, they are restricted to low register operands R0 to R7. They cannot use R0 to R12 because of the limited space in the instruction. You only got 16 bits, man. The 16 bits, you have to specify the operation and also which register the operation will be performed on. Okay, so if I use R0 to R12, I need more bits. Okay, so you have limited space. That's why some instructions limit you to using the R0 to R7 only. Okay, right. Good work, everyone. That's a lot of things to cover. Good job. Okay, do you have any questions before we stop here for today? Everyone okay? Class? Okay, sorry for the delay. Delayed 5 minutes, ended 5 minutes later. So I stopped here for today. Okay, if no questions, all right. So thanks everyone. Have a nice day. Okay, welcome. Bye everyone.